Chapter 4, we're going to be talking about properties of matter, chemical and physical properties, also chemical and physical changes. So, we have physical properties or chemical properties here that we will be talking about at first. Physical properties are inherent characteristics that can be determined without altering the composition. For example, a physical property would be its color, taste, odor, state of matter, density, melting point, boiling point. So basically things that you can see and observe. Chemical properties describe the ability of the substance to undergo a reaction with another substance or to decompose. So for example, here we have sodium metal and chlorine gas. They can react to make NaCl, which is sodium chloride, which is table salt. So physical properties of chlorine, we will talk about chlorine being 4 times heavier than air. Chlorine is a gas at room temperature. Chlorine is greenish yellow in color. Chlorine has a bad odor. Chemical change for chlorine would be this reaction that it can undergo. If you combine chlorine gas with sodium, you can make sodium chloride. So that's what sodium metal looks like in chlorine gas, and then obviously you can use it to make salt. So no two substances have identical physical and chemical properties. Everything is unique. So here are some physical properties that we can observe. Remember, we can talk about its color, odor, physical state, solid, liquid, gas, melting point in Celsius, or boiling point in Celsius. You don't really have to memorize this, but just an example. So for physical change are changes in physical properties such as size or density, and changes in states of matter without a change in composition. So its chemical composition doesn't change. There's no new substances being formed. So if you saw wood from a big piece into small little pieces, it's still wood. The chemical composition is still wood, even though it's smaller. So that's a physical change. So chemical change, on the other hand, we actually see a lot more changes where the composition of the new stuff is different from the old stuff. So if you, for example, if you take copper metal and you heat it in air, over time it turns into copper 2 oxide, which is kind of like it's called oxidation because an iron rusting is also called oxidation. So it's kind of like the rusting of copper in essence. So at first you have shiny copper, you heat it in oxygen gas and air, and then you will get copper 2 oxide. So that's a chemical change right there. Here are some common physical and chemical changes. We need to be able to distinguish between a physical or chemical change. The rusting of iron changes the iron itself from iron to rust, so it's a chemical change. Boiling of water is a physical change because there's no actual change of water. It just changes its phase. Any phase change alone is not a chemical change, just a physical change. Burning of sulfur, anything that's burning will always be chemical, okay? And you can actually see the observations. Yellow solid sulfur changes to gaseous choking sulfur dioxide. Boiling of an egg is also chemical because the liquid white in egg yolk, it changes to solid. It's actually chemical because you actually denature the protein in an egg when you boil it. So the chemical structure of the protein is changing, so it's a chemical change right there. Now we want to talk about combustion of gasoline, so it's also burning, definitely chemical. When you burn gasoline, it turns it into carbon monoxide, carbon dioxide, water, basically the usual combustion process. Okay, digestion of food is also chemical because obviously we're changing our food to liquid nutrients and partially solid waste, and we obviously absorb the nutrient. Sawing of wood, remember, one piece of wood to little pieces of wood is just a physical change because it's just changing the size of the wood, and you can reverse it by, I guess you can glue the wood pieces together, but they're still the same, it's still wood. Burning of wood is going to be chemical because it's not wood anymore, it turns to ashes. It says wood burns to ashes, gases carbon dioxide and water will also be released. Heating of glass is going to be physical because the glass still is glass. It's just you can change its shape. It's pliable, but it's still solid glass. It just heats it up. It's just warmer and you can change its shape, but it's still glass in essence. So that's a physical change right there. So the next question is, which of the following is a physical change? Grinding rock into powder. I would say yes, that is a physical change because it's still pieces of rock. Okay? A, that's physical change. Hydrogen and oxygen reacting to form water. That's a chemical change because it's a reaction. A shovel rusting. Rusting is a chemical reaction. An acid and base reacting to form water. That's a chemical reaction. So it's chemical change, chemical change, chemical change. Burning of sugar. Anything burning is also chemical change. So the only physical change we have here is A, grinding rock into powder. The next question, which of the following is a chemical change? Melting aspirin is literally just taking aspirin and changing its phase. So change of phase is not a chemical change. Breaking a plate, just breaking from one piece to small pieces, not a chemical change, physical change. So physical change, physical change. Boiling antifreeze. So if you boiled it, it's still antifreeze, but it's just a different phase, so still a physical change. Putting sugar in tea, you're literally taking a big piece of sugar, dissolve it in tea. Anything that's just dissolving is just changing phase from solid to aqueous phase. It is not a chemical change, it's a physical change. Lighting a match is burning. So this definitely is going to be a chemical change. E is our answer right there. So when we have a chemical change, we always write a chemical equation to represent the change that we have. Water, liquid phase, can decompose to hydrogen gas and oxygen gas. So a little bit about equations here. Reactants are on the left side, starting out. Products are on the right side. That's what you end up with. Okay, so produces, so the arrow means it goes towards the products. So when you have a chemical change, a lot of times there will be physical change accompanying it. For example, you have liquid turning to gas. But if it's just a physical change alone, might not be a chemical process. All right, let's talk about energy. Energy is the capacity of matter to do work. There's different kinds of energy. Mechanical, chemical, electrical, nuclear. We're talking mostly chemical energy here. Potential energy is stored energy due to its position. So the higher up it is, it has more potential energy. So something that's 20 feet above has more potential energy than when it's 10 foot above ground. A diver on a diving board has a high amount of potential energy because it's high up. Then the diver jumps down, the energy is converted to something else, potential energy. Kinetic energy is the energy that matter possesses due to its motion. A lot of times potential energy would convert to kinetic energy. So when you have water held by a dam and it's being released over here, potential energy is being converted to kinetic energy, and then we can use this kinetic energy to produce electricity. So when we want to measure heat as a form of energy exchange, because a lot of times our energy conversion, we release a lot of it as a form of heat, we use the unit joules to describe units for energy. And the energy to change temperature of 1 gram of water by 1 degree Celsius is 4.184 joules, and actually is 1 calorie right there. That's 1 calorie. The calories that we see on our food labels are actually kilocalories, kcal, and it's actually represented with C. So this is just 1 calorie. The one that you're looking at on the label is 1 kilocalorie, which is 1,000 times of this. So over here, we want to talk about heat and temperature. They're a little bit different. Obviously, they're related. If you have two beakers containing water, and then the temperature for both beakers is raised by 30 degrees Celsius. If your beaker has more water, it will require more heat to reach the same temperature. So for this one here, we want to use the reaction here to determine the amount of energy produced during combustion, and we want to use it in calories. So we'll have to change from kilojoules to joules and then to calories. So our conversion here is 1000 joules is 1 kilojoules because of kilo. Kilo is 1000 and 1 calorie is 4.014 joules. So if you need, this will be provided. And it says here it releases 802.5 kilojoules. So you take 802.5 kilojoules, you turn it to joules, put 1000 on the top, kilojoules on the bottom, cross off the kilojoules, and then you have 1000 joules here. We change it to calories by using this conversion, and your answer is 1.918 times 10 to the power 5 calories. So every substance has a heat capacity. What is the heat capacity? So specifically, we're talking specific heat of a substance is the amount of heat needed to change the temperature of 1 gram of the material by 1 degree Celsius. So water would take a different amount of heat to raise the temperature compared to something like aluminum metal. Aluminum metal would heat up a lot faster than water. So if you let a empty can of aluminum sitting outside in the summer by the pool, the can would warm up a lot faster than the water in the pool would. Like it says here, specific heat of water is much higher than most substances. Let's take a look. Water specific heat is 4.184 joules per grams per Celsius. So it's joules, 4.184 joules per 1 grams and 1 degree Celsius change. You see, alcohol is half of that. Ice is about half of that. Aluminum is really less than one, so less than 1/4 of it. 0.9. We got iron, that's even smaller. Copper is even smaller. Gold and lead is even smaller. That means gold and lead would heat up really, really fast. You just give it a little bit of heat, the temperature will change really quickly. Makes sense. Water will change its temperature the slowest because you need to put 4 joules in it before it can go up 1 degree Celsius. You only need to put 0.1 here for these guys for it to go up 1 Celsius per every 1 gram. And these are just units in calories, where we don't usually look at these for our calculations. We use joules here. But it's cool. You can see 1 calorie here is 4.184 joules. So specific heat capacity is right here. When we use it to calculate energy, we want to talk about heat. Heat equals to the amount of substance, mass of it, times the specific heat capacity, times the change in the temperature. So this little sign, delta sign here, indicates the change. It means final temperature minus initial temperature. So I'm going to give you some symbols here to remember. Heat is Q. Mass, we always sometimes just write M for it. And then specific heat, I like to write it as CS. And then delta T is final minus initial. So let me write that down. So it's final temp minus initial temps. So I like to say Q equals to MCS delta T. So when we talk about delta T, one important thing is earlier in a few chapters there we were converting Kelvin and Celsius. Remember Kelvin and Celsius, we were talking about the conversion, like 0 Celsius is 273 Kelvin because you always just plus 273. And then if you had 273 Kelvin, you want to get it in Celsius, you just minus 273. But when we do delta T, if it says 5 Kelvin, because it's talking about the difference, and we talked about how the Kelvin scale and the Celsius scale is exactly the same size because it's 100 here, but this one would be like 180. It's completely different. So Fahrenheit is going to be different, but lucky for us, we don't really use Fahrenheit for our calculations here. We usually use Celsius and Kelvin. So for Celsius and Kelvin, remember, if it says the delta T is 5 Kelvin, the delta T is also 5 Celsius right there. You don't have to convert. So a very common mistake is they take, oh, if my delta T is 5 Celsius, I think my delta T is 278 Kelvin. That's really, really wrong because if you think about it, 278 Kelvin is such a big difference, right? It's like this is only 5, 278 is so big. 5 Kelvin and 5 Celsius is the same size. So just think about that. So from like 0 to 37, from 273 to 310, you see how it's the same size? And right here is 37 Celsius. This will be 37 Kelvin. From 0 to 100 Celsius, that's 100 Celsius, the delta T. The 100 Kelvin, that's the delta T. So just keep that in mind. Now, the next thing is when we talk about specific heat capacity, here's questions that we can probably see. How much heat is needed to raise the temperature of 200 grams? So they put a decimal place there to specify three sig figs. 200 grams of water by 10 degrees Celsius. So we know that delta T is 10 degrees Celsius, and the mass is 200 grams, and the specific heat capacity of water is 4.184 joules per gram Celsius. So what you want to do is you want to make sure if you put your units in there, they all cancel out and you get heat in terms of joules. It's very important because if they were to give you change in temperature in Kelvin, you'd want to make sure you change the Kelvin to Celsius. But remember, delta T, Kelvin and Celsius, exactly the same number. So you just got to remember to change the units if you had to. But in this case, we don't. In class, we'll try to do some different units so we can work on converting these units together. So 200 grams times 4.184 joules per gram Celsius. So the grams and this gram cancels off because this is on the top, that's on the bottom. And the Celsius here is on the bottom over here. And that Celsius is on the top, so they cancel off too. Okay, so our answer is going to be left over in joules, and it's going to be 8.37 times 10 to the power 3 to signify 3 sig figs right there. All right, so next question we have, calculate the specific heat in units of joules per gram Celsius of an unknown if 1638 joules raises the temperature of 125 grams from 25 degrees to 52.6 degrees. So we need to get each part. Remember, Q equals to M CS delta T, and my M is 125 grams. My T, delta T, remember, is final temperature minus initial temperature. So 52.6 minus 25.0, you get 27.6 degrees Celsius. And the heat over here is going to be 1638 joules. What we have to do is solve for the specific heat. So let me write the equation out, and then you can see why you solve your specific heat like this. Let's see. Let's write it out. So Q is 1638 joules. That equals to M, which is 125 grams. And then we don't know what the CS is, so that's what we're saying is we don't know. And my delta T, we calculated is 27.6 Celsius. Okay, so you see how you have a CS left over there? So the CS is on one side here. So to get the answer, we'd have to divide both sides with 125 and 27.6. So CS would be 1638 joules divided by 125 grams and divide by 27.6 degrees Celsius. Now be really careful. Try this on your calculator. Make sure you're doing it correctly. If you're putting it into your calculator, you must put a parenthesis between these two terms. Otherwise, your calculator will do 1638 divided by 125 times 27.6, and you get the wrong answer. Make sure you come up with 0.475 here. So let's erase this, write this neatly. Joules per gram Celsius. All right, next question. Here's a question that says, how many joules of energy are required to cook an omelet in 5.0 kilograms of iron skillet that was heated from 25 degrees Celsius to 150 degrees Celsius? And they gave us a specific heat of iron as 0.452 joules per gram Celsius. So in this case here, we want to make sure we use our formula. So let's write it out again. Q equals to mCs delta T. Okay, and we're looking for Q because we're looking for energy, which is the heat energy. So Q equals to M. What's my M? It's in kilogram. 5 kilograms, we have to convert it to grams because you see my units here, it's in grams. So 5 kilograms to convert to gram, how would you do that? So I'm going to go ahead and write this out over here. So 5.0 kg. To turn it to grams, I know 1 kg has 1,000 grams. So we can just do that right there. Okay, that's my mass. And then my CS, I'm just going to write it down. 0.452 joules per gram Celsius. You see how joules is on the top, gram Celsius is on the bottom. And you see how kilograms is crossed off. Now you have grams. And this gram crosses out with that gram. Okay, and then my delta T is final temperature minus initial, which my final is 150.0 Celsius minus initial of 25.0 Celsius. So let's see what that gives us. If you put all of that together, so over here, obviously, that's 125. Okay, you take 5.0 times 1000 times 0.452 times 125. You should get an answer that's really, really big in number. I'll write down all the numbers. It's 282,500 joules. Okay, so you see how I have 282,500 joules, and then I have my work here. This is 2 sig figs, 5.0 kg is 2 sig figs, so that's 2 sig figs right here. There's 3 sig figs, and this one is 1 decimal place. I kept 1 decimal. This is 4. So out of 2 sig figs times 3 sig figs times 4 sig figs, I will keep only 2 sig figs. So if I'm keeping just 2, I'm going to round down to 28 and then keep all these to be 0. So my answer in this case would be C. Let's talk a little bit about energy and chemical changes. Chemical reactions, they either absorb energy or release energy. Okay, they can produce different kinds of energy. Electrical energy we use in a battery, heat and light energy when fuel undergoes combustion, but obviously we use it to move our cars, or sometimes we just heat the place up, right? So chemical changes can use energy. So that one's producing energy. This is using energy. So we use electricity to decompose water. We use solar energy. Plants use it anyway during photosynthesis. So all kinds of ways we can use the energy or we can release the energy. Absorb it to do the reaction or release it during reaction. Next, we want to talk about conservation of energy. Energy can be changed from one form to another form, but you cannot create or destroy it. It's just always constant. You can only change from one form to another form. And a lot of times we actually lose energy in the form of heat because the conversion is not very efficient. So sources of energy for us in real world, we use petroleum as a source a lot, coal, woody plants, but petroleum deposits, so we use it to make gasoline and natural gas for us. And we have petroleum is made of hydrocarbons. Hydrocarbons means it only has carbon and hydrogen. Obviously, the name tells you that, carbon and hydrogen. Okay, so let's take a look at some hydrocarbons. Here's a table for some common hydrocarbons here, simple ones. Methane is CH4, ethane is C2H6, propane is C3H8. So we hear of methane a lot and propane a lot, and butane too, we hear about that. C4H10, we have pentane, C5H12, hexane, we will use in lab sometimes, C6H14, heptane, C7H17, H16, octane, C8, H18, nonane, C9H20, decane, C10H22. You don't really need to memorize this, but these are just some form of hydrocarbons that we have. Now we want to talk about natural gas. It consists mainly of methane, which is a form of hydrocarbon, with small amounts of ethane, propane, and butane mixed in. So coal is formed from plants, and it remains stored under high pressure for many years. The higher the carbon content, the more energy available in the coal. So carbon content is important on there. So let's take a look at this question here. It says, if I have 12 grams of solid carbon reacting with 4 grams of elemental hydrogen to produce natural gas, because we just talked about how natural gas is mainly CH4, how much carbon and hydrogen are needed to make 100 grams of natural gas? So we need 100 grams, okay? And let's take a look at mass ratio of carbon to hydrogen. Remember we were talking about the law where the mass has certain ratios. So this one here is always going to be, this is 12 grams to 4 grams. So this would be 3 times the amount and the mass of hydrogen. For every time there's 4 grams of carbon, there's 12 grams of 4 grams of hydrogen to 12 grams of carbon. That means 1 gram of hydrogen would be to 3 grams of carbon. So it's 3 to 1 ratio. So let's write that down. So our mass ratio here is 3 grams of carbon to 1 gram of hydrogen. And that's if we were doing just total of 4. And then if we had a total of 16, it would be 12 grams of carbon to 4 grams of hydrogen. How did I know that? I just took 12 divided by 4. So I got the ratio 3 to 1. Okay, so then what I want to do is I got to break this into 4 pieces. 100 grams broken into 4 pieces. Each piece is going to be 25 grams. So that means I'll have 25 grams of hydrogen here, and the leftover will be 75 grams. So I would pick my answer to be A. All right, so all different forms of energy, because we keep increasing our energy usage, we need to come up with new renewable energy sources like wind and solar and biomass. So a lot of research is being worked on so we can have higher efficiency solar sources of energy, maybe better solar panels, solar batteries are made for it that last longer. We also have nuclear energy, biomass, wind energy is pretty clean, and synthetic fuels. And that is the end of our chapter.